everyone. Welcome to this video on comparing and ordering numbers. Many business applications involve ordering and comparing numbers. This is why this video exists, because you'll be doing a lot of this type of thing. Just for some examples, in information systems management, scripting languages, which are computer programming languages, are used to control repetitive processes. These kinds of scripts rely on if-then statements that branch based on comparing two numbers or quantities. So depending on the comparison that's made, something is done or something else is done. For example, an admin might write a program to monitor licenses on a server, looking to see whether any have expired. This program would involve a comparison between the current date and the license expiration date, and returning a message to the administrator based on that. Number comparison between dates in that case. Excel itself has if-then functions to perform actions like these on data in spreadsheets, which are widely used across business applications. So those functions can apply if this number exists in this column, then do the calculation on that column. If this number in this column is less than that, then do this other thing. These types of things happen all the time when using Excel. And Excel is, as I keep saying, ubiquitous in business. Internal rates of return, which are just numbers that you'll learn about how to calculate, are compared in finance to decide which projects to invest in. Finally, when using statistics, you will repeatedly have to compare tiny numbers called p-values and significance levels to see which is smaller. If you don't do that correctly, you'll make the wrong decisions. If you don't do these comparisons correctly in all of these cases, you will end up making the wrong decisions. These are but a few examples of how comparisons are used in business, and I hope I have convinced you it is a necessary skill. Before we dig into this topic, we have to go over some notation for making comparisons. This notation comes up in all of the contexts that we have so far mentioned, and refreshing it will be helpful. These actually are operators. We looked at mathematical operators in our operators and order of operations lectures. These operators are often called the logical operators because they let you make statements that then can be true or false. So table 4 shows notation for making comparisons. You see this symbol with the double equal sign or just a single equal sign. That, in the context of making comparisons, means equal to. So the equal sign, you're used to that meaning equal to in an equation, but the double equal sign is often used as a logical operator in programming. This is to avoid confusion. Not equal to can be represented by a slash followed by an equal sign, or by the not equal to symbol, which is an equal sign with a slash through it. Greater than or more than is this symbol. The greater than sign followed by the equal sign, or the two combined, as you see on the right-hand side, is greater than or equal to. Then we have the less than operator, and then less than or equal to formed in the same type of way as greater than or equal to, with a less than sign followed by an equal sign, or the less than or equal to sign that you typically see in mathematical texts. Why do we need to know this notation? This notation is used to build statements that read from left to right like sentences and use mathematical notation instead of words for efficiency's sake. For example, suppose you compared the numbers 7 and 2. Using the notation in table 4, all of these following statements could be said and all are true. 7 is greater than 2. You could say that quite simply in the notation with just 3 symbols. Then 7 is also greater than or equal to 2. That's also a correct statement. 2 is less than 7. That's true. 2 is less than or equal to 7. That's also true. And 2 is not equal to 7. So notice that that list of mathematical statements using the notation would be less than 1 line long. If you use all of those words, it's a whole paragraph. Hence, notation is frequently used for brevity. But these days, this notation is used constantly in order to interact with computers. Computers will understand mathematical notation, whereas words, they will not. Let's start doing comparisons by talking about comparing positive and negative numbers. Negative and positive numbers exist on a continuum that can be represented with a number line as shown in figure 9. So what you see here is your usual number line. I'm sure you've seen a million of these. It is a horizontal line that extends infinitely to the left and infinitely to the right, but is normally just written with two arrows, one at each end, to indicate that it continues. The numbers are normally written underneath, and the notches show where those numbers actually go on the number line. The notches or the hatch marks. There's different words for those little vertical lines. The key with a number line, the really, really useful thing about a number line is that numbers get smaller as you move to the left, and numbers get larger as you move to the right. This is true no matter where you are on the number line. The number line, as we're looking at it, also shows another important feature of numbers, which is their symmetry around 0. So 0 is sort of theoretically the center of the number line if you think of the number line going from left to right. To the right of 0 are the positive numbers, the counting numbers, 1, 2, 3, 4, 5. Also, though, to the right of 0 are all the subdivisions between those numbers. So 1.1 is on this number line. 2.4 is on this number line. They're not written in, but they are there because those subdivisions are understood to be there when you look at number lines. To the left of 0, you have the negative numbers. And notice the symmetry. One step to the right of 0, you have the number 1. One step to the left of 0, you have the number -1. That 1 in both of those numbers is indicating how many steps away from 0. So taking a look at 2, you see that 2 is 2 steps to the right of 0, whereas -2 is 2 steps to the left of 0. So the sign on the number is giving you a direction to go, whereas the magnitude of the number is telling you how many steps away from 0 you are. To get just that magnitude out in calculations, you use the absolute value, right? But we're not going into that here or yet. So to reiterate, numbers get smaller moving to the left and larger moving to the right. This means that if you correctly place two numbers on a number line, you will reliably know which one is smaller because it will be the one on the left. The one on the right is the larger one. Taking a look at example 5.1, we're asked which number is smaller, 4 or -5? Further, we're asked to write the answer in mathematical notation. So having just recommended the use of number lines, I'm going to go ahead and draw one. Because this is one of our earlier examples, I'm going to go ahead and write in all of the numbers on this number line that I'm going to need. I'm going to start with the positive numbers, 0, 1, 2, 3, 4, and then the negative numbers, -1, -2, -3, -4, -5. I'm going to throw one on to the left, -6. It's one smaller than -5, and up here I'll put a 5, just so we're clear that they continue. So which number is smaller, 4 or -5? Let's mark them both on the number line. 4 is here, -5 is here, -5 is to the left, so -5 is smaller than 4. Now we're asked to write this answer in mathematical notation. We could do it a few different ways. I'm just going to pick two. -5 is less than 4. That's the literal mathematical translation of this sentence. We were asked which number was smaller, so it makes sense to write the answer this way. You would not be wrong to write 4 is greater than -5. That's exactly the same statement. If you flip the order of the numbers, you have to flip the order of the inequality, inequality being the less than or greater than symbol, in order to preserve the truth of the statement. 4 is greater than -5 because 4 is to the right of -5 on the number line. Taking a look at example 5.2, which number is larger, -18.4 or 0.9? Write the answer in mathematical notation. So a couple of things before answering this. I want to point out 0.9 and -18.4, they are not on this version of the number line in the sense that they are not labeled on the version of the number line that we used in example 5.1. The thing about number lines is subdivisions exist as small as you want to make them. What do I mean? Well, take a look at this number 0.9 and consider that I could write just a portion of the number line with 0 at the left end, 1 at the right end, subdivided into 10 equal length sections. Now, each of these represents a tenth. 0, 0.1, 0.2, 0.3, 0.4. This would be 0.5, 0.6, 0.7, 0.8. This would be 0.9. So to put 0.9 on the number line, you have to think of the subdivisions between 0 and 1. What about putting negative 18.4 on a number line? I'm going to draw another subdivision of the number line. I'm going to start at negative 18 and go down to negative 19. Halfway between those two would be negative 18.5. Subdividing still further, between the negative 18 and the negative 18.5, we would get negative 18.1, negative 18.2, negative 18.3, negative 18.4. Because I don't have any space here, I'm going to write it down below. So that is how subdivisions work, and you can get them smaller than this. You can divide each step of 1 into hundreds or halves or anything. Any subdivisions are possible. But notice that if you are in the positive direction, your numbers are going up in the positive direction. If you're in the negative direction, your numbers are going down in the negative direction. So this would be negative 18.6. This would be negative 18.7, negative 18.8, negative 18.9, negative 19. How does this help us order these numbers? Well, instead of doing all these subdivisions and things that I've been doing, I'm just going to, this time, put some key features on this number line, because you don't want to have to write out every single little tenth in order to make a simple number comparison. Here I'm going to put my 0, here's my 1, and so 0.9 would be somewhere close to that 1. Then here on the negative side, I'm not going to place in a whole bunch of numbers. I'm just going to realize that negative 18.4 is way below 0. So maybe I'll place a negative 5 here just so we get the idea of why we're going in this direction. Here we go with a negative 10. And so negative 18.4 is going to be somewhere down here. For the purposes of this problem, you really don't need more detail than where that 0 is. But I've put in a little more detail so that we can have a little bit of context for this. So from the number line, we see that 0.9 is to the right of negative 18.4. This means that 0.9 is larger than negative 18.4. Now, how would we say this statement in mathematical notation, as we've been asked to do? We would say 0.9 is greater than negative 18.4. You could certainly write an equivalent statement that negative 18.4 is less than 0.9. Notice once again, if you flip the order of the numbers, you must flip that inequality. So the greater than must become a less than. And that's simply to preserve the statement as being true. If you don't flip the inequality, you're going to make that statement into something that's not true. These two examples demonstrate something that is always true, that you can put in your pocket and count on, and that is that any given negative number is smaller than any given positive number. This can be seen on the number line, where all of the negative numbers are to the left of all the positive numbers, because all the negative numbers are to the left of 0, and all the positive numbers are to the right of 0. So really, example 5.1 and 5.2, knowing that this is always true, we could say, well, 4 is greater than negative 5, and 0.9 is greater than negative 18.4, simply because 4 is positive and negative 5 is negative. 0.9 is positive and negative 18.4 is negative. However, the review of number lines that we went through to do those examples is going to come in very handy.